Okay. So, this is a graduate seminar, is that?
Well, it's a graduate class, but this day is a graduate seminar, so.
Okay, so you're not gonna be tested over this. So, you can watch it at leisure. And, you know, I'm a great believer in a really good problem should keep you awake at night. And, what I'm gonna talk about today, this talk was written to be for a more general audience, and when Jim asked me to come in and talk to you all, I looked at it and I thought, well, I didn't do a good job of aiming it towards a general audience, so I think it's more in the ballpark that you all ought to be able to understand it. Now, I know many of you work in the general areas that Jim is interested in, and this is kind of a tangential subject that's more in group theory and combinatorial algebra, but it's a concept, the Davenport constant of finite abelian group. Really, I should just say finite group, but what I'm going to talk about today is restricted to finite abelian groups, is a fundamental tool in factorization theory, as is this thing up here called the cross number. Now, the Davenport constant is very easy to understand. The cross number is much more difficult. And if I was going to give you a series of talks, the next talk would be about the applications of the cross number in factorization theory. I'm going to present it. I'll talk a little bit about what its application is, but to really appreciate it, you have to get into algebraic number theory, which I think in an hour today would be too much for me to do. Okay, but let's talk about what the Davenport constant is. I think this thing works. Well, it was working a second ago. Well, nothing's working.
Let me come.
The talk may consist of one title slide.
Try it now.
Yeah. What happened?
I just clicked on the mouse and make sure that.
So it was your fault.
Yeah,
Okay.
probably.
If you like this talk, there's an old paper. This is in a conference proceedings, so it's about 30 years old. On the Davenport constant, the cross number, and application of factorization theory. I'm sure it's in the library here. It's so old, I think I have a copy, but I'd have to look for it pretty hard to find it. Now, I will start at really an elementary level, probably too elementary for you all, but let's go ahead and start, and quickly it'll shift into a more abstract setting. Here's a list of what? 7 numbers. And I just kind of arbitrarily picked some numbers. And let's ask a question about these 7 numbers. Can I choose a subset of these integers whose sum is divisible by 7? So ideally, if I was giving this talk to a more general audience, does someone want to come in?
They're in.
Yeah, okay. I would give everybody a minute to get out paper and pencil and start around with this, right? Or get your calculator out. Because, given a few minutes, you figure this out very quickly. Because the answer is yes. Okay, and there's a lot of different ways to do it. There's 3. There's actually probably more than that up there, but 333 and 458 is 791, which is 113 times 7. And there's 2 other examples down there. So the answer is yes. So I'm starting with a positive question, right? Has a positive answer. But let's change the numbers a little bit. Let's reduce it down to 122, 32, 386, and 458. And I'll ask the same question. Is there a subset of these numbers, a proper subset, not empty, whose sum is divisible by 7? And unlike slide number 1, where the answer was yes, this answer here is what? No. Okay. Why? Well, there's a much easier way to do this, as most of you probably understood without me telling you. Just take these numbers and reduce them mod 7, right? So it reduces down to what? 1, 1, 1, and 3. So you really only have to look at the residue classes, right? Okay. Is there a subset, a subsum of these three numbers that's divisible by 7? And clearly the answer is what? No. Okay. And I mean, it would just take you a minute to scratch through all the subsums, and you'd see that, 1 and 1 is 2, 1 and 1 and 1 is 3, continue on. And you don't get something that's divisible by 7. Okay. So what's the moral here? The moral here that this is really a problem in Z mod 7, hence it's a group theory problem, rather than just a sum problem. And we'll ask a more general question here. Because in the first case, the answer was yes, in the second case, the answer was no. How many elements must be in a sequence of elements in Z7 in order to guarantee that it contains a subsum that sums now to what? 0, right? It's a bunch of numbers divisible by 7 in Z7 would sum to 0. So the observations are that from the last slide, 4 is what? Not enough, right? Is 7 enough? Notice on the first slide there were 7 numbers. Okay, well, let's see if we can answer that question. So, to answer it, let me make sure we're all on the same page, which I think we are. But just to make sure, there are 2 ways to write down a finite abelian group. Be it its invariant factors. So again, if I have a finite abelian group, I know that it can be written as a direct sum of cyclic groups, Zn1 plus Zn2 plus ... Znk, where the indices divide each other on the way up. N sub I divides N sub I plus 1 as I varies from 1 up to what? K minus 1. And these integers are called the invariant factors, and that's going to be important in this discussion here in a few minutes. But there's another way to write your finite abelian group down, canonically, is that there's a unique set of prime powers, p sub 1 to the s1, p sub 2 to the s2, ... p sub t to the st, where the pi's are not necessarily distinct primes, and the si's not necessarily distinct positive integers, such that you can write G out as a direct sum of cyclic groups of prime power order. So these are 2 distinctly different things. The pi's to the si's here are known as the elementary divisors. This is something you'd see on your qualifying exam in algebra. So I'm going to focus at first on finite abelian groups written in terms of their invariant factors. And towards the end of the talk, I'll switch and start looking at the group written out in terms of its elementary divisors. But I just wanted to make sure that, again, we were on the right page together here. Okay. Now, some definitions. Given a finite abelian group G, the value of K from the invariant factor representation is known as the rank of the group. So a cyclic group always of what? Rank 1. Okay. I'll refer to G written in form 1 as the invariant factor form of G, and I will refer to G as written in form 2 as the elementary divisor form of G. These forms seldom match, as you probably well know. For instance, they do not if G is cyclic, not of prime power. So if P and Q are distinct primes, then Z mod PQ, you probably saw this in your undergraduate abstract algebra course, is what? ZP plus ZQ. So you've got, again, the 2 representations are different. Okay. Some of our favorite finite abelian groups, because when I define the Davenport constant in this cross number and I start looking at it, as in almost any algebraic setting, I'm going to look at it in some fundamental situations. So what are these fundamental situations? If the rank is 1, so in cyclic groups. If the rank is 2, so G is Z mod N1 plus Z mod N2 with n1 divides n2. So what's a good example of that? The good old Klein 4 group. Each ni is a power of a fixed prime. Such a group is known as a P group. Okay, so G is isomorphic to Z mod P to the m sub 1 plus Z mod P to the m sub 2. So again, the P is fixed there. I'm writing this out in terms of invariant factors.
And
So
I guess
cyclic
the P
groups-
groups are a good example where the forms do coincide.
That's right, okay. So cyclic groups, rank 2 groups, and we're gonna talk in great detail about rank 2 groups and in a few minutes, rank 3 groups and P groups. Okay, so those are gonna be our favorite groups today that we're gonna start picking off and talking about. Now, what I wanna do is take what I did on the first couple of slides and do it in a little more generality. So here comes the definition. Take a finite abelian group, take a subset, and it's important that we're talking about sets here because I'll kind of shift back and forth between sets and sequences, but in everything I do today, the order doesn't matter. Okay, so suppose you have a subset of elements from your finite abelian group. I'm calling it S up here. Okay, G sub 1 down to G sub T, and these are elements that are not necessarily distinct. You have repetitions. S is called a zero sequence in the group if the subset sums to what? 0. Okay. It's called a minimal zero sequence or an MZS if it contains no proper sub-zero sequence. Now, I'm going to focus on minimal zero sequences, but there's certainly a difference between zero sequences and minimal zero sequences, and we'll get to that here in a minute. I'll look at some examples. Now, in general, if I've got any people in here that like to do things that aren't abelian, which I tend to not do, you can define these two things for non-abelian groups. What I'm about to do in the non-abelian case gets really complicated, and I'm not the one to talk to you about it. Okay, so you can invite Alfred likes non-abelian stuff, so he can invite somebody else in to talk about the non-abelian case, but that's going to be left to somebody else. But I refereed a paper once on computing the Davenport constant for maybe the symmetric group on 5 generators, and it was 40 pages long, and it was a mess. Okay, so in the non-abelian case, one reason I like what I'm about to get into is in the abelian case, there's a lot of really nice things that happen. I can't think of anything in the non-abelian case here that's really nice. Okay, but they happen. So if you're interested in that, you can look at some papers. You can look up some papers about the Davenport constant in symmetric groups, because I know there are a few papers like that. So if I have a minimal zero sequence, let's say written like this, I'm going to call the number of elements in that sequence the order of the sequence. So when I say order of S is equals to T, that means I'm looking at a sequence with T elements in it. If I let big B of G represent the set of zero sequences of G, I'll let U of G represent the set of minimal zero sequences. Now I'm going to count these regardless of order. Okay, so order here isn't going to matter. I know I already mentioned that, but okay. Now, for those of you that have worked in factorization a little bit, theory a little bit, I'm using B of G here because this is known as the block monoid. I'm not going to get into the monoidal structure this morning, but these zero sequences do form naturally a monoid, with the operation being just concatenation of the sequences. Now, if you glue two zero sequences together, what do you get? Another zero sequence. So they form an additive monoid, and the atoms of that additive monoid are these elements in the set I'm calling U of G, the minimal zero sequences. This monoid is a great example of when non-unique factorization fails. And I could talk a lot more about that, but I'm going to stick to the combinatorial part of this today, the Davenport constant. And did I skip a slide? No, and the cross number. Okay, now let's look at some examples, some basic examples of zero sequences and minimal zero sequences. So again, pick a non-zero element in your group G, and let's suppose it has order n. Okay. Be careful, I redefined that a second ago for sequences. This is for an element. Then take the sequence made up of k times n copies of G, where just k is some positive integer. Okay, it's a zero sequence, right? N copies of G added up together is 0, and so k copies of that is 0. So that's a zero sequence, and moreover, if k is 1, it's what? It's a minimal zero sequence. And so in Z7, 7 copies of 1 sums to 0. It's a minimal zero sequence because no sub piece of that one sums to 0. No non-empty piece of it sums to 0. Okay. So in particular, in Z mod n, which I'll write the elements of Z mod n as congruence classes like this. One popular minimal sequence is what? N times n copies of 1. Okay, and I'll pull that one out from time to time and talk a little bit about it because it's a very simple minimal zero sequence, and it's a good thing to use when you're trying to build examples. You know, the base example usually relates back to this minimal zero sequence. Okay, so not only is it a zero sequence, but importantly, it's what? It's minimal. Okay. Here's another really nice minimal zero sequence. Maybe even simpler than the first one. Take any non-zero element and then look at the sequence what? GG inverse. That sums to what? 0. Okay. And obviously no subsum of it sums to what? 0. So there's a nice minimal zero sequence. Maybe even simpler than the first one. Now, this is something that early in my career I wasted a lot of time. Well, waste isn't a good word, because we never waste our time, right? Even when you have something and it doesn't do what you want it to do, oftentimes you see that it does something else. I got interested in building minimal zero sequences in Z mod n, which is something better left to a number theorist or a combinatoricist. But I goofed around with it a lot. And so what was I trying to do? Take a positive integer n, and then take this, a bunch of non-negative integers that sum to n. Okay. So in other words, take a partition of them. And if you know anything about partitions, there's when you start counting partitions, things go crazy really fast. So look at the sequence m sub 1 bar, m sub 2 bar down to m sub k bar. In Z mod n, that's going to be what? It's going to be a minimal zero sequence. Now, why is it minimal? Well, because these things sum to n, so no subsum of it's going to what? Sum to n. It's a minimal zero sequence in Z mod n. Now, again, I'm going to borrow this from kind of combinatorial number theory. The number of partitions of an integer is asymptotic to this thing. So as n gets big, the number of partitions is not nice. Okay, it grows exponentially. You know, if you're interested in the question, how many minimal zero sequences does Z mod n have? You can start computing that number, and when you get to like Z11 or Z12, the computer starts to cough. Okay, it's not something you'd have to go to your computational people to get help to do this. I think early in my career, I thought maybe this is nice. Maybe there's a nice pattern as to how many minimal zero sequences there are. This is just a small piece of that puzzle, and it's not nice. So the general question isn't nice. So the number of minimal zero sequences in Z mod n, even if n's, what word do I want? A reasonable integer is probably astronomically big. Okay. Now, let's talk about another minimal zero sequence that is a natural one to look at, but a lot more complicated than the last 3 or so that I've looked at. And there's a lot of ways to write this down, and I don't think I've ever found the best way to write it down. This is the best way I know of to write it down. So here's my little finite abelian group. Well, actually, it might not be little, but at least written like that. Looks little, okay? And I'm going to view this like we're in linear algebra, okay? I'm going to let EI be the element of G consisting of 1 in the ith coordinate and 0 everywhere else. So just like basis vectors in linear algebra, okay? Now, let's look at this sequence. I'm going to go to the first coordinate, look at E1. I'm going to take n sub 1 minus 1 of those. Then I'm going to go to the second coordinate and do the same thing. I'm going to take n sub 2 minus 1 copies of E2. I'm going to do that in every coordinate. And if I add all those up, I don't get 0 back. But I can get 0 back by what? Throwing the sum of these things onto the end. Because look, now I've got what? N sub 1 E1s. I've got n sub 2 E2s. I've got n sub k EKs. So when I add that up, I get a what? A 0 sequence, and it's not hard to argue that it's minimal. This could be like problem 1 on the Davenport constant test. You know, argue that that's a minimal 0 sequence. If you take any piece of it, any proper piece, you're leaving some things out that you need to zero some coordinates out. That's a very bad argument, but it's generally what you need to do. Okay. Now, I love this. I absolutely love this guy, this S. Okay. And I'm not the only one, as I'll show you in a few minutes. So just to give you a little better idea, if you were in Z3 plus Z6, what would this thing look like? 1 0 1 0 0 1 0 1 0 1 0 1 0 1, and then what? 1 1. So there's a minimal 0 sequence in Z3 plus Z6. Okay, and note that in general, if I take this SG, how many elements are in it? Well, there's n1 minus 1 plus n2 minus 1 dot 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 n sub k minus 1 plus what? 1. So you get the summation as I goes from 1 to k of n sub I minus 1 plus 1, which you can write like that if you want. I usually think about it like this. Okay. But look, what does this tell you? That in this group, there is a minimal 0 sequence that is at least what? That big. Maybe there's one that's bigger. We don't know yet. But there's at least one that big. Okay. Now, taking one small liberty, which I'll talk about in a few minutes, here comes the big definition for the first 3/4 of the talk. Let G be a finite abelian group. The Davenport constant of G is the longest length of a minimal 0 sequence. So look, if you take a finite abelian group, and I'll show you in a second, it's easy to argue that there are finitely many minimal 0 sequences. Now, I've already convinced you that finite might be big, but it's finite. Okay? So this set over here is finite. So take the maximum of it. We're going to call that the Davenport constant. Davenport was a famous number theorist. This definition seems to have emerged in the 60s at a conference that was in his honor for like his 65th birthday or something like that. And, you know, this is one of these things that when you first start playing with this, you say to yourself, okay, let's take a finite abelian group. Let's compute its Davenport constant. Oh, that's not going to be hard, right? It's really hard, because I'm going to convince you. In fact, there's no known closed formula for doing this. And there's a couple of really big open problems about it that I'll get to in a few minutes. But I'm going to use this big D of G to represent the Davenport constant. So again, what is the Davenport constant? It's the longest length of a minimal 0 sequence in your finite abelian group. Okay. Now, first theorem, and I use the word theorem kind of lightly here, because this is one of my favorite theorems, because I love the proof of this that I'm going to show you in a second. For many years, I worked on this committee that wrote the advanced portion of the GRE, and I always snuck, we write the exam, and I always snuck something related to this onto the exam. And for one reason is because of the argument I'm about to show you. So first comment here is that the Davenport constant can't be any bigger than the order of the group. Okay, now why? Here we go. Proof in one slide. 1, 2, 3, 4, 5, like 6 or 7 lines. Here we go. Suppose you've got a minimal zero sequence of length bigger than, here's my first typographical error, that should be what? Order of G. Okay. Thus, take an element that's not zero. Okay. Oh, I'm sorry, each element up here is not zero. Okay. Now I'm going to form a sequence of elements. I'm going to call them gamma 1, gamma 2, down to gamma k. I'm going to let gamma 1 be the first element in the sequence. I'm going to let gamma 2 be the sum of the first 2 elements in the sequence. Gamma 3 would be the first 3. Gamma k would be all of them. Okay. Here we go. Since none of the gamma i's are 0, gamma sub I equals gamma sub j for some I bigger than or equal to j. In other words, k is bigger than the order of g. There's got to be 2 elements on this list that are equal. Okay, so gamma I and gamma j have to be equal for some, let's say, I strictly bigger than j. So if I set these 2 things equal to each other and subtract the shorter sequence off the larger, I get a sum of the gi's that's what? 0, which contradicts the minimality of S. Okay, there is a subsequence of this that sums to 0, so contradiction. So you can't have a minimal 0 sequence of length bigger than the order of the group. So you see that and you think, oh, this can't be so hard, right? The order of the group's the upper bound. And look, the proof's really simple. It could be like problem 2 on the Davenport constant test. Okay. But first of all, this opens the door for some really simple observations. For a cyclic group, the Davenport constant is what? N. Why? Well, because the Davenport constant is less than or equal to n, and 1, 1, 1, 1, 1 n times is a what? Minimal 0 sequence. So the Davenport constant of a cyclic group is the order of the group. So far, everything's what? Everything's great. Everything's easy. This is great. All right. Oh, I actually proved that, right? There's your minimal 0 sequence of length n in the cyclic group. Okay. Moral. Computation of the Davenport constant on a cyclic group is trivial. Okay. So if you're someone that's just in the cyclic groups and no other groups, you can stop listening because I've talked about everything that you're going to be interested in. But if it's not cyclic, then the fun begins, right? Exclamation point. And you don't have to go far to see where the problems start. Let's go to your favorite, well, I'm being, maybe I'm taking too many liberties, assuming that the Klein-4 group's your favorite non-cyclic group. But one of my favorite non-cyclic groups is the Klein-4 group. So let's look at the Klein-4 group. It turns out that the Davenport constant of this thing is 3. Okay, and this is something you can convince yourself of very, very quickly. Why? Try to build a minimal 0 sequence of length 4. Okay. What happens? Well, pick an element. I'll just arbitrarily pick 1, 0. You can't pick it again. Why? Then that would be a 0 sequence. Okay, so you got to pick something else. Let's take 0, 1. Well, you can't pick 0, 1 again because that would be what? A 0 sequence. So you've got 1 element left. Pick it. And that's a 0 sequence. So the Davenport constant of the Klein-4 group is 3 instead of 4. So that's the longest minimal zero sequence in the group Z2 plus Z2. Now, let's return to our general case here. Again, I've written G out in terms of its invariant factors. I constructed a minimal zero sequence in there, right? And I called it what? S sub G. That was the thing with all the copies of the coordinate vectors in there. And there's how big it is, right? Okay. I'm going to call that D star of G. And you know enough math at this point to be suspicious. If I'm calling this D star, this is probably different than D of G, right? Or I'm going to prove that they're equal, one of the two things. Well, let's state something obvious first. If you have a finite abelian group, then what? D star is less than or equal to D of G. It's what? It's the length of a minimal zero sequence. There could be something bigger, there might not. We don't know yet. So you get that inequality, and we have that inequality from the first result. So D star of G is less than D of G, which is less than the order of G. And this is really kind of what makes the rest of the discussion here about D of G work, is you can find references to this conjecture in the literature. You can look in a couple of my papers to find references back to it in number theory books. But I was fortunate early in my career to see Erdős speak, and he was not a great speaker. The problem was, by the time I saw him, he was way up in his 80s. He'd just go to the board with a piece of chalk and write really, really slowly. It was actually kind of painful to watch, but he was really famous. And so we watched him. But he got interested in this problem. This is kind of a combinatorial number theoretic type problem. And he looked at this, and he conjectured in the 60s that D of G is what? Equal to D star. Now, to convince you of how hard a problem this is, first of all, tell you that the conjecture is not true. But it took 5 or 6 years for somebody to find a counterexample. Now, I think if we didn't know anything about this and someone walked in here today and made this conjecture, they could go over to your computational algebra people, and they'd have the answer by the end of the day because of the computers they have now. In the 60s, you didn't have the computing capacity that you have now. And this is not a good computing problem because of the number of minimal zero sequences. This is an intensive computing problem. So just trying to grind through and solve problems like this with a computer, if you can find some mathematics to reduce the problem, it might work, but in general, it's going to be hard to do this. So this was Erdős's conjecture. There.
I hope that whole thing wasn't that way. I would think that Bradley would complain, but.
Bradley's new.
All right, so, what's going on here?
That's a good question. Okay.
trying to get this back to full.
The other was explore.
Yeah.
There you go. All right, proceed.
Are we good?
Yeah, good.
Alright. So there's the counterexample group. Z2 plus Z2 plus Z2 plus Z2 plus Z6. What's its rank? 1, 2, 3, rank 5. Okay. And if you really want to know, there's the counterexample. There's no, when you can sit down and look at this for a while. And you might think, well, there's got to be like a pattern to see how he did this, and I really don't think there is one. But there is your minimal zero sequence that is this is okay. This is a sequence of length 10, which is not a zero sequence and doesn't contain a minimal zero sequence. So what you can do is sum those up, look at its inverse, throw the inverse in, you get a minimal zero sequence of length 11, which is bigger than 10. Okay, that's how he did it in this technical report that I have a copy of it. If anybody would want a copy of it, get in touch with me. I'll run it off for you. But this is the group of smallest known order, for which the Davenport constant is strictly bigger than D star. Okay, so look, it's a group of order 96. I can't even imagine how many minimal zero sequences are in there. It's astronomically large. So again, computationally, this is a tough problem. Now, this is actually a problem I was interested enough in that myself and one of my colleagues gave this to some RAU students one summer and said, okay, in his technical report, he does not compute the Davenport constant of this group. He just shows that it's bigger than what? 10. So he disproved the conjecture. But nowhere in the report does he compute the Davenport constant. Now, it does turn out, so you'll see that here's the group, okay? And we can generalize the group by taking what? K copies of Z2 and adding it on to Z3. So the version of this up here, 1, 2, 3, 4, that we were looking at would be K is 4, but suppose K is at least 5. Well, no, I'm sorry. This is Z6, so there would be another Z2 there. You wrote it like this. So we'll start at 5. I did have some students first argue using the computer that the Davenport constant of that group is 11. And they were able to do the next one. When K is 6, they got B12. Oh, and you get real excited after you see 7, right? It's 13, and then you don't get excited because at 8 it's what? It's 15, and then at K equals 9, the computer explodes. Okay, computer, well, at least when we were doing it, the computer exploded. If we were computer freaks, we might be able to do better, but this is really hard computationally. Okay. That's the smallest known counterexample. Here is the smallest known counterexample by rank. Z3 plus Z3 plus Z3 plus Z6. So this has rank 4, but it's bigger than 96, order 96. It's a bigger group, but it's of smaller rank. Okay. This is the group of smallest rank, rank 4, for which it's known the conjecture fails. Okay, and here we go. Really great paper. It's in the very first volume of the Journal of Number Theory. It's by a number theorist who was in Wisconsin named Olson. And he proved that if G is a finite abelian group of rank less than or equal to 2, then D of G is equal to D of G star. Okay. It's about 6 pages long. It's not a simple argument, but it's a beautiful argument. I highly recommend looking at that paper and working your way through the argument. It's really, really beautiful mathematics. Okay, but now let's glue the first couple parts of this slide together. I've got a counterexample of rank 4. Everything of rank 1 or 2 isn't a counterexample, so there's an obvious question here, right? Is there a counterexample of rank 3? Or for rank 3, does D of G always equal to what? D of G star. It's not known. It's open. And you can find paper after paper after paper where people take a group of rank 3, they say if it looks this way, they argue that D of G equals D of G star. But the problem's open. It's not been solved. Do I recommend that you work on that? I don't know. It's been worked on a lot and not cracked. I think if you're going to approach it, you need it to use a much different approach than anything that anyone's.
I think that's a post-tenure problem.
Yeah, that's a post-tenure problem, but it's a good problem. Because you think to yourself, you know, how complicated can a group of rank 3 be? Well, guess what? It can get very complicated. You'll find out really quickly. Okay. Now, that's what I have to say. How much time do I have? It's 10 to 11.
Yeah, like 9 minutes.
Okay, so I'll do a little bit of this. If you like factoring things, this is a function that you should get familiar with. Now, my slides mislabeled up here. I'm still talking about the data. So there is a large class of groups for which it's known that this D of G is equal to D of G star. Okay. So theorem in any of the following finite abelian groups, I'll say the conjecture works. Okay. This is Olson's theorem, rank less than or equal to 2. It works for P groups. The same guy proves it in the next volume in Journal Number 3. And that's a really nice argument too. I don't think it's as nice as the rank 2 argument, but it's a really, really nice argument. Okay, and then there's these kind of cases that you can cherry pick and get things to work. If something's of the form Z2 plus Z2 plus Z2 plus Z2M, where M is odd, that ends up working. That might be kind of a hint as to where this Dutch guy got the counterexample, because it would be like the next index out. Z3 plus Z3 plus Z6M, where the greatest common divisor of 3 and M is 1, and this thing. So you could get on Math Science Net and find 20 papers and keep this list going. Okay, but again, in general, the problem's open, but there's been a lot of work done on it. Okay. Here are 2 recent results involving Davenport's constant that are really kind of analytic number theory arguments, but this is, I list these just to give you an idea of how deep this gets. In 1990, in discrete math, this Israeli mathematician, Meshushalom, proved that the Davenport constant, again, write your group in invariant form. It's bounded above by nk times 1 plus log of the order of G over nk. Okay, so again, as you can see, this gets pretty involved. And in 2007, I believe this paper is in the Israel Journal. This is a Russian mathematician, Dmitriev. He showed that the Davenport constant divided by D star is less than or equal to ck log k to the k for some absolute constant k. And again, remember, k is what? The number of summands up here in rank. And those are both really deep analytic number theory papers. They're not simple combinatorial arguments. So here's an obvious problem, which probably obviously doesn't have an answer. Given a finite abelian group G, find a formula for D of G. And again, you know, you can do this if you narrow down the kind of groups you're looking at. In general, it's probably not possible to do it, but again, I don't think anyone can say either way at this point. There is an easy formula or there is not. Okay. Now, I'm almost out of time, but let me show you something related to the Davenport constant, which conceptually is harder to swallow, but the problems relate to factorization theory very, very well. So I'm going to stay in the world of looking at finite abelian groups and minimal zero sequences. So, suppose you've got a finite abelian group, and suppose I'm not going to restrict myself at first to zero sequences, to minimal zero sequences, but let's just look at zero sequences. I'm going to call the cross number of this zero sequence. When I first started looking at this, I would stare at that thing and say to myself, how did someone ever think to start looking at this? Because its applications are so deep, it's kind of like what came first, the chicken or the egg? I mean, I would have never thought to look at this function, but here it is. Let's look at the sum of 1 over the orders of all the elements in the zero sequence. This is called the cross number of G. And I can again go into the minimal zero sequences, which is a finite set. Look at all the cross numbers, say, let's find the biggest one. And I'm going to call that big K of G. And that's what we call the cross number of the group G. Okay, now I think, where did this come from? Well, this is maybe something that you all, in the work that you do, might really be interested in. The cross number is a key tool in studying the factorization properties of rings of algebraic integers, like z bracket root -5, your really basic example of something that's not a UFD, but is an HFD. And more general objects known as chromons. The details of that would have to be in another talk, but it turns out that if you go into this set of zero sequences and you look at this thing as a function from that set into the positive rationals, it's a homomorphism. If you apply it to the concatenation of 2 zero sequences, it's the cross number of the first one plus what? Cross number of the second one. All right, now, let's look at some simple examples, and maybe in these first couple of examples, I can show you why this is interesting. Here is Z4. Z4 is a great group because it's maybe the last one that only has a few minimal zero sequences. And there they all are. Okay, I'm leaving my bars off of my elements. But 4 copies of 1, 4 copies of 3, 2 copies of 2, 3, 1, 2, 1, 1, 2, 3, 3. You can sit down and convince yourself that's all the minimal zero sequences in Z4. Look at what their cross numbers are. They're all 1 except what? That one, which is what? Half. Now, what's special about that? That's this thing that I constructed by what? Taking an element and then looking at its what? Its inverse. Okay. Now, again, the only reason 2 didn't behave that way is 2 is its what? Its own inverse. Okay, these 3 has a different inverse than itself. Okay, so everything was 1 except this one value gave me a half. Okay, now let's do the same thing for the Klein-Ford group, which has fewer zero sequences. Okay, so you get 2 copies of 0, 1, 2 copies of 1, 0, 2 copies of 1, 1, and then our favorite thing that what gave me the Davenport constant back. Look at what happens now. 1, 1, 1, and then what? 3 halves. So the first one, the only one that wasn't 1 was a half. And the second one, the only one that wasn't 1 was bigger than 1. Now, since I'm out of time, I'm going to have to cut this off here, but just let me give you the theorem that if I kept going would eventually poke its nose out of this. And this is a theorem of a guy that Jim and I know, Uli Krauser, a German mathematician, is that, so if you look at the biggest value of the cross number on this first example, it's 1, right? So the cross number of Z4 is 1. The cross number of a group turns out to be 1, if and only if it is prime power cyclic. So this is prime power cyclic, it's what, 2 squared. So take your favorite prime power cyclic group, 25. What? 121. Those all have cross number 1. If you're not prime power cyclic, something like this happens. You can build a minimal zero sequence whose cross number is bigger than 1. That's a really beautiful argument. It's in one of Willie's papers. And I'm about out of time. I have a little bit more, but I'm going to stop here. If you have any questions, I'd be happy to answer them. He has these slides if anyone wants them. And we're done here, right?
Let's give him a hand. Anybody have any questions?
I have a question for you, Dr. Cornell. Is it, correct me if I'm misremembering, I think you know, Jared presented in a GSS a while ago, and he gave proof that Jared,
Okay.
This is
that the Davenport constant is n if and only if the group is cyclic. Is that
Oh,
correct?
equal to the order, yes, that is correct.
yeah, that's correct.
Yeah. And the other direction is not terribly hard, but it's harder than the forward direction, but it's not too hard.
Yes.
Do we allow the empty set to be zero sequence?
Okay, I don't, but people do, which is why I think I muttered about it a couple of times, but I don't. You know, the empty set's the empty set, right? Yeah.
So this block mono that you were talking about, that mono is atomic?
Yes, the monoid is zero sequence. It's on the block. They call it the block monoid. Yes, it's atomic.
How
And
about,
there's all kinds of things known about it.
Okay.
Yeah.
So if you have a zero sequence that is not minimum, is necessarily the sum of two minimum?
Yes, absolutely. And it's easy to look in block monoids and take zero sequences that can be factored. Like, lots of different ways, lots of different lengths.
any questions for the folks watching out there? Bradley or Ansa, tell me, could you hear the entire time or was it ever muted? You can speak up if you
They're
like.
muted.
Well, they're muted, but they can
It-
unmute.
I always can. Yeah, I can hear everything.
Oh, you didn't hear it?
I did hear everything.
Oh,
You
okay.
did hear it.
Good. I think that muted thing that came up was just incidental off of, yeah. All right, well, thank you all. I will see you on, I guess I won't see you on Monday, right? I'll see you on Wednesday, so.
Monday's a holiday.
That's right.
Oh.